Hello. Today we're going to talk about proofs with similar triangles. Unfortunately, I can't be to school today to make this video, and my printer ran out of ink, so it's a little light, but I think we can make things work out just fine. Again, we're going to work on proofs, so students will be able to write a formal proof whether two triangles are similar is your objective. And as we look at the first problem here, we know that BD and AE are drawn to intersect at C. So this information is really important. We also know that the two lines are parallel. So let's mark that up. AB is parallel to DE. We know these intersect at C. Now, why is that an important fact? Well, when you have intersecting lines, you end up with vertical angles. And if you have vertical angles, you have one pair out of the two necessary to prove that something is similar. And so this is going to be a formal proof, so we'll have statement and reason. So I know that BD and AE intersect at C. That would be a given statement. And the other important fact is AB is parallel to DE. That is also given. And eventually what we're trying to do is we're trying to prove that the two triangles are similar. And again, it's kind of set up nicely, so I can claim that ACB is congruent to, now I do need to make sure I have my corresponding parts here. A corresponds to E, so ECD, vertical angles are congruent. The next part is this parallel lines piece, and you can actually use a couple different angles. You can either look at B, compare it to D, or A and compare it to E. And it doesn't ultimately matter because we know that we only need two angles to make the angle-angle theorem true. If we have all three, then that's even nicer, but it's a result of the triangle sum theorem, and we can derive it regardless. So here I have the first angle. I'm just going to pick angle A. So let angle A be congruent to angle E if parallel lines are cut by transversal, alternate interior angles are congruent. So that's the reason why I'm able to claim that A is congruent to E. The final thing I'm going to do is triangle A, B, C is similar to, and again you've got to make sure that you get these corresponding parts right, triangle E, D, C by the angle-angle theorem. And now if we wanted to, and these were truly similar, you could go through and you could like measure and determine the scale factor, but that's not the point of this. This is just to prove two triangles are similar. Again, this gets cut off. What you have here is a triangle M goes down to, it looks like N, T, R, and P, W, S. So this must be the P, here's the W, there's the S. So hopefully that gives you the image that you can see and work from as you're drawing your proof out. Now there's a few important pieces. One, you can see that RT and NP are perpendicular, and then SW and NP are perpendicular. What you can't see is that they claim that MN is congruent to NP. And you might be asking, well, why does that matter? Well, that's really quite important for us as we start thinking about this, because that implies that we have an isosceles triangle. And if we have an isosceles triangle, then we know base angles are also congruent. So there are my base angles, because base angles of an isosceles triangle are congruent. And so again, we have a formal proof, so we'll start with our statement. And we'll go with our reason. And you can always turn any formal proof two-column into a formal proof written in paragraph form. They are normally a little more poetic, but not required. So what is our given? We have M, N congruent to MP. We also have RT perpendicular to MP. And we have SW perpendicular to NP. Make sure you let the person know that there are segments. This was a given. This was a given. And this was a given. All right. How does that help me? Well, I can actually claim that the measure of angle RTN is equal to 90 degrees, perpendicular lines. Perpendicular lines form 90-degree angles. Similarly, the measure of angle SWP equals 90 degrees, perpendicular lines form 90-degree angles. Okay, so we'll put that right there and there. What does that mean for us? Well, the measure of angle RTN is equal to the measure of angle SWP by substitution. Then what I have to do is claim that triangle MNP is isosceles, which is by definition of isosceles triangle. And really where that comes about is because MN is congruent to MP, and then angle N is congruent to angle P, base angles of an isosceles triangle are congruent. All right, so we've got two angles congruent, so now we have similar triangles. So triangle NTR is similar to triangle PWS by angle-angle theorem. You've proven that these two triangles are similar. Okay, the last problem that I want to go over is just a sequence of transformations. Make sure that we understand how to do these as it pertains to the grid. It's real basic and sort of tough to see. And again, I apologize, my printer ran out of ink literally on this page. So we'll do the best that we can to make this visible to you. This is transformation. The first thing I'm going to notice is that I have the rotation piece. Okay, about 90 degrees. And since that's closest to DEF, that's what I have to work from. And so essentially, as I draw the lines, I'm going to make that perpendicular, keeping the distance exactly the same. I'm going to swing it counterclockwise 90 degrees. And so this point to -1, it's going to hit here at 7, 0. The next one I'm going to look at come down like this. So we got to get those lines exactly perpendicular for the same distance. And finally F. It's got to just be a little bit off. So that's F prime, D prime, E prime. And obviously not the formal way Mr. Hessep would like you guys to go through this. Rulers, protractors, all of which are still at home. So again, what are the important aspects of having a rotation? You have to have the point. You have to connect this and then swing it 90 degrees counterclockwise because that's positive, and make sure that's a 90-degree angle, keeping the exact distance the same between parts. The next thing that we're going to do is we're going to dilate it out. And so the dilation comes from point A, because it says A right there and a half. So essentially I can draw these rays emanating from A, and then I just have to have the distance. So that would be E double prime F's double prime and D's double prime. And so my finishing triangle looks something a little bit like that. How do I know that they're similar? Well, it was a sequence of transformations, including a dilation. I could measure each of the angles. I could compare the distance of DF to F prime D prime, F prime E prime, compared to F double prime E double prime, and make sure that they're all the same. Okay, so some of the takeaways away from today would be the way we used our proof and our theorems, definitions, and properties to be able to prove that a triangle was similar, and just an example of how you can use a sequence of transformations to prove that two shapes are similar. You sort of backtrack the sequence. So if I was going to prove that D double prime, E double prime, F double prime is similar to the original, I'd first have to dilate by 2 and then swing a 90 through the point A. Okay, thank you for your time.